Welcome to this explainer. Today, we're going to trace the ultimate origin story of the physical universe. And honestly, we're not just talking about some distant, dusty galaxies today. We are uncovering the deeply personal, literal connection that you and I have to the cosmos. Let's dive right in. Seriously, I want you to literally look at your hands right now. Think about the heavy elements that make up our daily lives. You know, the gold on your ring finger, the iron coursing through the hemoglobin in your blood, the calcium in your very bones. Where do they actually come from? Because, as we're going to see, they didn't just magically appear out of nowhere when the Earth formed. Which brings us to part one, the mystery of our origins. So, back in the early universe, things were pretty basic. It was essentially just a giant soup of hydrogen and helium. The crucial point here is this. Basically, nothing heavier than lithium existed initially. Literally no carbon for life, no oxygen to breathe, no silicon for rocks. That means a massive, universe-spanning manufacturing process had to happen to create the building blocks of our planet, and, well, by extension, our bodies. And that leads us to part two, stars as cosmic factories. The core of a star is essentially the ultimate pressure cooker. You have this absolutely immense gravity pulling everything inward, constantly trying to crush the star. Now, this gravity creates such extreme pressure and heat at the center that it literally forces atomic nuclei to merge together. This is nuclear fusion. It's the process that releases the energy making a star shine, but more importantly for us, it's the exact mechanism that forges entirely new elements. Let's look at how this builds step by step. A massive star spends most of its life just turning hydrogen into helium. But when the hydrogen runs out, the core contracts, heats up even more, and starts burning helium into carbon, then carbon into silicon, and finally, silicon into iron. You can kind of imagine the star like a giant cosmic onion, building up layers of increasingly heavier elements inside its core as it ages. Moving right along to part three, the iron dead end. Now, what's really fascinating here is the totally unique nature of iron. Iron is actually the most tightly bound nucleus in the entire periodic table. Extracting energy by fusing iron is literally physically impossible. In fact, it costs energy. So the moment the core becomes pure iron, the nuclear furnace just shuts off. That outward pressure that's been fighting gravity for millions of years, it simply vanishes. And this is where things happen in an absolute split second. Without that outward pressure, gravity takes over completely. The entire core collapses inward at unimaginable speeds. It gets so unbelievably dense that electrons and protons are literally crushed together to form neutrons. The density skyrockets until the core cannot be compressed a single millimeter further. And then, it violently bounces back. It acts exactly like a tightly coiled spring that has suddenly been released. Which takes us to part four, supernovae, the ultimate forges. We need to carefully contrast two distinct types of these explosions, mostly because they give us completely different chemical gifts. On the left, we have the core collapse supernova we just described. That violent bounce creates a flood of neutrons, rapidly forging the rarest, most precious elements in the universe, like gold, silver, lead, and uranium. But on the right, we have a type 1a, or thermonuclear supernova. This happens when a dead star called a white dwarf steals way too much matter from a neighbor and just completely detonates. This specific explosion is nature's primary factory for creating massive amounts of iron. To truly understand a supernova, you really need to grasp the sheer scale of the energy involved. Just look at this mind-blowing number, 2 × 10 to the 43rd power joules. That represents the kinetic energy released in a single core collapse supernova. Let's put that massive number into a pretty terrifying perspective, actually. That is the energy equivalent of taking the mass of 5 entire suns and throwing them outward at thousands of kilometers per second. And here is the truly crazy part. That kinetic energy, we can actually see, it represents only about 1% of the explosion's total energy. The other 99% is carried away by ghostly subatomic particles radiating out into the void. Absolutely wild. Here we are at part 5, seeding the interstellar medium. So this apocalyptic destruction is actually an act of beautiful cosmic creation. The explosion sends shockwaves blasting outward at thousands of kilometers per second. All those newly forged elements, the carbon, the oxygen, the gold, the iron, they are thrown out of the dead star's core and into the empty void. As these shockwaves sweep through space, they compress and heat the thin interstellar gas. Over millions of years, the supernova acts as a kind of cosmic fertilizer, chemically enriching the entire galaxy with heavy elements. And this brilliant data illustrates exactly how we know this is all true. We are looking at a visual fingerprint of our galaxy's history. It shows the ratio of alpha elements, things like magnesium and calcium, compared to iron. Now, in the first billion years, the primary explosions were fast-burning massive stars, which are really rich in alpha elements. But as time went on, slower developing white dwarfs started exploding, suddenly flooding the galaxy with iron. That causes that super dramatic shift you see on the right side of the chart. The data perfectly tracks our origin story.
Finally, part 6, we are made of stardust.
Those ancient drifting gas clouds, the ones heated and fertilized by the explosive deaths of massive stars, well, they didn't just float around forever. Over eons, gravity pulled those chemically enriched clouds back together. They collapsed, spinning and flattening to form a new disk. In the center, a new star ignited, which is our sun, and the remaining dust and heavy elements smashed together to form planets, to form Earth. Which leads us to this totally inescapable, profound conclusion. We are the living, breathing remnants of dead stars. Every ounce of iron in your blood that carries oxygen, every speck of calcium in your teeth, every single bit of carbon that forms the structure of your cells, it was all forged in the belly of a massive star and blasted across the galaxy in a supernova explosion billions of years ago. So, I'll leave you with this. The next time you walk outside and look up at the night sky, don't just see distant, disconnected lights. Realize that you are inextricably linked to them. Do you now realize that you are not just in the universe, but that you are the universe, finally waking up and looking back at itself? Thank you so much for joining me on this explainer, and as always, keep looking up.
Welcome to This Explainer. Today, we're diving straight into what is arguably the most mind-bending paradox in astrophysics. We're going to figure out how the absolute darkest voids imaginable are, surprisingly, responsible for creating the most brilliant beacons of light in the entire cosmos.
You know, black holes have this reputation, right? They're known for being these terrifying, pitch-black voids where gravity is so intense it just swallows absolutely everything. Not even light gets out. So, how is it physically possible that these exact same cosmic sinkholes are the engines powering the brightest, most luminous objects in existence? I mean, it sounds like a total contradiction.
Section 1. Illuminated accretion disks. To actually solve this mystery, we have to look just outside the black hole itself. We need to shift our focus to a violently active area right on the edge, kind of like a cosmic waiting room. So when gas, dust, and matter get pulled toward a black hole, they don't just drop straight in like a rock into a well. Thanks to angular momentum, all that stuff gets caught up in a high-speed, swirling orbit around the center. We call this swirling vortex an accretion disk, and as that gas spirals closer and closer, it loses orbital energy. This exact physics process is where the magic of light creation actually begins.
Think about how the gas behaves inside this disk. You've got massive amounts of material totally jammed together, and different layers are rotating at completely different speeds. This makes the gas rub together incredibly violently, generating extreme friction. It's literally like rubbing your hands together on a cold day, but scaled up to an unimaginably powerful cosmic level. All that friction converts kinetic energy into intense heat and ultimately blinding light, way before the matter ever crosses the event horizon, the point of no return.
And this intensity, it just keeps building as the gas gets closer to the center. When this super-fast gas hits the inner edge of the disk, it encounters what we call a boundary layer. Right there, the gas abruptly slows down. Imagine slamming on the brakes at near light speed. That sudden, violent deceleration takes all that pent-up orbital energy and instantly converts it into a massive release of heat and light. It creates this localized zone of just extreme, glowing radiation.
Section 2. Quasars and lighting the universe. Okay, we've seen how this works on a smaller, stellar scale, but now let's scale things all the way up to the absolute monsters lurking right at the centers of galaxies. We are talking about supermassive black holes here. Honestly, the scale of these things is kind of hard to even wrap your head around. They pack staggering masses, up to 100 million times the mass of our own sun, 10 to the 8th power. Because their gravity is so intense, the accretion disks surrounding them are incredibly massive and unimaginably powerful.
And these supermassive black holes are the actual engines powering quasars. Quasars pump out an overwhelming amount of radiation, especially in the UV spectrum. But here is the really fascinating part about the scaling. Compared to a regular stellar black hole, the inner edge of a quasar's accretion disk is actually about 100 times cooler. But, and this is a big but, because the total surface area of that disk is so unbelievably massive, the quasar ends up shining roughly 100 million times brighter. They become these ultimate cosmic beacons that easily outshine all the billions of stars in their host galaxies combined. It's wild.
So here's a crucial question. With all this matter rushing inward, creating all that friction and light, where does it go when the black hole gets full? Because there's a serious bottleneck. Not all of this material can actually fall into the black hole at once. The outward pressure from the extreme radiation, mixed with immense magnetic forces, actually pushes back. It's literally like trying to force a blasting fire hose into a tiny kitchen funnel. It's going to back up. Section 3. The birth of plasma jets. When that black hole's waiting room gets a little too crowded and the pressure becomes totally unsustainable, the system needs an exhaust pipe to relieve the tension. And, well, the universe came up with a pretty spectacular solution. That solution? It's all about magnetic fields. You see, the accretion disk is deeply threaded with these powerful magnetic lines. As the disk spins at crazy speeds, it drags those magnetic field lines right along with it, twisting them up tighter and tighter, almost like a giant invisible python coiling up. This intense twisting action physically grabs the superheated gas that couldn't fit into the black hole, violently squeezes it, and accelerates it straight outward, completely away from the black hole.
And what's really cool is these magnetic field lines aren't just chaotic, they're highly structured. They actively contain the outward flowing gas. So instead of a messy explosion blasting out in every direction, these twisted magnetic fields focus that superheated plasma into tight, insanely fast, narrow beams. They literally shape the flow of the material.
And when I say fast, I mean relativistic speeds. In systems like the binary star SS433, we've observed these focused plasma jets being fired out at a jaw-dropping 26% of the speed of light. 26%! That's over 75,000 kilometers per second. It is just a phenomenal release of kinetic energy, all directly fueled by the black hole's gravity and that magnetic twisting.
But the most amazing thing is we don't just theorize this stuff. We actually see this exhaust system in action across the universe. We can spot smaller systems firing off twin jets, and we also capture incredible radio images of massive relativistic jets erupting from supermassive black holes, jets that are literally plowing right through intergalactic space, traveling outward for thousands of light years. It's unreal.
Now, as this impossibly fast jet travels outward, it doesn't just glide cleanly through space. Eventually, it slams into the sparse, quiet gas of the surrounding universe. And when it hits, the smooth, uniform kinetic energy of the jet's core totally transforms. It creates this chaotic, violently hot shockwave, inflating what astrophysicists call a cocoon of turbulent plasma. That violent interaction kicks off even more radiation, specifically synchrotron radiation, which ends up lighting up vast stretches of empty space in radio waves.
Section 4. The ultimate cosmic engines. So, putting all of this together, it's really time we fundamentally rethink these incredibly dense objects, because they definitely aren't just cosmic endpoints.
Black holes are not just cosmic vacuum cleaners. They are the grand architects of cosmic light. Far from being these ultimate destroyers that just trap light forever, black holes are actually powerful creators. Through the chaotic friction of their accretion disks and the unfathomable power of those magnetic plasma jets, they are fundamentally responsible for illuminating our universe. They literally shape galaxy evolution, they heat up intergalactic gas, and they shine brighter than anything else we have ever observed.
Which brings us to one final thought. If the darkest voids in a universe are, ironically, the exact things creating its brightest beacons, it really makes you wonder, doesn't it? What else is hiding out there in the dark, just waiting to be understood? I'll leave you to ponder that incredible cosmic paradox. I really hope this explainer sparked your curiosity to look a little deeper into the night sky. Thanks for joining me, and keep exploring.
Hello everyone, and welcome to the Explainer. Now usually, we'd start off with a nice, tidy agenda. But today, yeah, we're tossing that right out the window. We literally need to plunge straight into a massive, totally mind-bending mystery about the universe we live in. You know, we usually look up at the night sky and think of it as this perfectly predictable, beautifully stable clockwork system. But what if I told you that right beneath that calm exterior lies a terrifying, completely invisible threat? It's a pretty provocative question, isn't it? Is our solar system a ticking time bomb? I kind of want to shatter your assumption of a peaceful, stable cosmic neighborhood right out of the gate here. The reality?
at least according to some insanely complex astrophysics, is that our seemingly solid, dependable world is actually dancing right on the razor's edge of ultimate destruction. And the craziest part? The trigger for this catastrophe has been hiding in plain sight the whole time.
Okay, let's dive into this. Part 1. The illusion of a clockwork universe. So, to really understand this hidden threat, we first have to look at the baseline we've all been taught for centuries, right? Isaac Newton's reliable clockwork physics. Under purely Newtonian physics, if you isolate just a single planet and the sun, the math is, well, it's absolutely beautiful. The planet's orbit forms a flawless, eternal elliptical loop. It just keeps going around and around on that exact same path. There are literally no surprises. If our solar system was just the Earth and the sun, we would be entirely safe forever, period.
But we aren't alone, which brings us to part 2, the hidden chaos of gravity.
So here's the fatal flaw in Newton's perfect little picture. Planets aren't out there by themselves. They actually pull on one another. And the real danger here lies in a fascinating concept called resonance. Resonance happens when the orbital frequencies of two planets magically align mathematically, like when small whole number ratios start linking their movements. When this happens, a tiny gravitational pull doesn't just happen randomly anymore. It happens at the exact same point in the orbit, over and over and over again, eventually accumulating into a massive system-altering force. Think of it kind of like a cosmic puppeteer. Jupiter, with its absolutely massive gravity, can rhythmically tug on a tiny planet like Mercury all the way from across the solar system.
And this brilliantly illustrates what that actually looks like. Because of all these little gravitational perturbations from other planets, a planet's orbit doesn't stay locked in place perfectly. As you track it over thousands of years, the long axis of that orbital ellipse actually rotates. It shifts completely unpredictably over time. Basically, it's wobbling. And when that resonance we just talked about locks in, well, that wobble can quickly spiral totally out of control.
Which leads us directly into part 3, a recipe for cosmic disaster.
Now you might be thinking, this is all just theoretical math, right? Well, no. Astronomers Jacques Lascar and Michael Gastineau actually used supercomputers to literally predict the ultimate future of our solar system. But predicting a chaotic system is insanely difficult. To mathematically calculate the solar system's movements up to 40 million years from now, you need to know the current exact position of the planets down to an error margin of just 15 meters. Okay, but what if you want to predict up to 60 million years? You have to know where the planets are right now down to 15 millimeters. Because of this chaos, calculating past 60 million years is technically impossible. Literally, a 15 millimeter mistake today completely changes the entire outcome of the solar system.
So how do you bypass this impossible 15 millimeter problem? Well, Lascar and Gastineau took a statistical approach. They set up the current solar system, made microscopic variations to the starting positions, and ran 2,500 different possible futures using strictly pure classic Newtonian physics. They basically simulated the end of the world thousands of times over to see what would happen.
And here is the first massive shock. In about 1% of these pure Newtonian futures, Mercury goes completely rogue. Because of that rhythmic resonance with Jupiter we talked about, Mercury's orbit gets incredibly stretched out over time. Its orbital eccentricity dangerously exceeds a value of 0.7. Now, what does that mean? It means its path becomes a highly stretched, super elongated oval. And once it hits that extreme shape, it actually starts crossing the paths of the other inner planets.
So the absolutely crucial point here is that Mercury isn't just some tiny rock that gets quietly tossed out into the void. Oh no, it acts as a massive trigger. When its orbit stretches past that 0.7 mark, it totally rips apart the stability of the entire inner solar system. First, it pulls on Venus. Then, Venus's orbit destabilizes, which then completely throws Earth's orbit into chaos, and finally Mars gets dragged right into the fray. It's an apocalyptic, system-wide domino effect.
The climax of these Newtonian simulations is, well, it's nothing short of horrifying. In those 2,500 simulated futures, Mercury obliterates Venus 86 times, and it crashes directly into Earth 34 times. Let that sink in. Under pure Newton math, our planet is basically playing a cosmic waiting game with absolute destruction.
But wait, part 4, Einstein saves the world.
Obviously, we are still here, right? So why? Well, a tiny microscopic detail from 20th century physics swoops in as the ultimate plot twist. It turns out Albert Einstein's theory of general relativity is the literal savior of our planet. As the researchers noted, if it weren't for the incredibly slight effect of Einstein's corrections to gravity, humanity likely would not exist in this universe at all.
Now, what's truly fascinating about this is exactly how unimaginably small this correction actually is. General relativity tells us that massive objects warp spacetime. For Mercury, which is moving really fast deep down in the sun's gravity well, this introduces a tiny mathematical correction factor, velocity squared over the speed of light squared. We are talking about a factor of roughly 10 to the negative 8th power. That is 0.00000001. It's a microscopic warp in spacetime, but it alters Mercury's path just enough to matter.
Let's compare these two cosmic fates side by side. Under Newton's math, the resonance between Jupiter and Mercury goes completely unchecked, pulling the planets into those dozens of fatal collisions we saw. But under Einstein's relativity, that tiny, practically invisible warp in spacetime shifts Mercury's orbit just a fraction of a hair. It acts like a cosmic speed bump. It desyncs Jupiter and Mercury, completely disrupting that deadly resonance. When the researchers ran the exact same 2,500 simulations again, but this time with Einstein's equations included, the collisions basically vanished. Out of all those futures, there was only one single near miss where Mercury exceeded that dangerous 0.7 threshold.
And that brings us to our final takeaway. Part 5, our fragile cosmic oasis.
When you really step back and think about the sheer mathematical luck required for this system to stay together, it forces you to ask, why does this matter for you and me? It means that our totally solid, dependable, everyday world is actually living right on the razor's edge of cosmic chaos. Our planet's survival over the next 4 billion years, until the sun eventually expands anyway, doesn't actually come from some unbreakable, bulletproof law of perfect orbits. It hinges entirely on a fragile, totally bizarre, relativistic quirk of spacetime that just barely keeps Mercury in check. It honestly leaves you in awe, doesn't it? So, I want to leave you with this final thought today. We look out into the deep universe hunting for other planetary systems, right? Looking for signs of life. But if our own existence relied entirely on a microscopic, 1 in a million warp in spacetime, just to stop our planets from playing a deadly game of cosmic billiards, how many other worlds out there in the dark simply weren't so lucky? Keep looking up, folks, and never ever take our stable little sky for granted. Catch you next time.
Welcome back to a brand new Explainer. Today, we are skipping right past the standard glowing stuff in the cosmos. The stars, nebulas, and galaxies you're already totally familiar with. Instead, we're going on a little detective hunt to explore the hidden, invisible architecture of space itself.
It almost sounds like a sci-fi movie pitch, doesn't it? What if the most powerful forces in the entire universe are completely invisible to our eyes? Well, in astrophysics, we really can't just rely on things that glow. We actually have to look for the gravitational footprints they leave behind. Because when we look out into the night sky, those beautiful luminous objects, they literally make up just a tiny, tiny fraction of what's actually out there. The vast majority of our universe is dominated by an unseen side, just working silently in the background, completely shaping the destiny of everything we know.
Okay, let's dive right into this cosmic mystery. We're going to follow 3 main clues today: gravitational lensing, dark matter, and dark energy. We'll start with what we can actually observe, and then work our way out to the invisible engines that are quite literally driving the universe.
So let's kick things off with our very first major clue: gravitational lensing. Now, you might be wondering, how on earth do we find something that's completely invisible? Well, we look for how it messes with the things we can actually see. Think about looking through a thick glass of water. The water's there, right? Because the light passing through it bends, and the objects behind it look all warped and distorted. Out in space, gravity acts in a very, very similar way. A supermassive gravitational field acts exactly like a giant cosmic magnifying glass. It literally slows down and bends the path of light traveling from super distant stars and galaxies.
And this brilliantly illustrates exactly what we're talking about. See, a normal, perfectly shaped glass lens focuses light rays down to a single, neat little point. But out in space, mass is super messy. It's unevenly distributed. So a gravitational lens bends light paths in a much more complex, chaotic way. The light rays get crossed up, they diverge, and they never actually meet at a perfect focal point. And that causes massive, wild distortions in the image that eventually reaches our telescopes here on Earth.
Now, if you're the kind of person who loves peeking at the math behind the curtain, this is for you. This is the refractive index for a gravitational field. And what this formula actually tells us is absolutely mind-blowing. We usually think of light traveling at its maximum absolute speed through the vacuum of space, right? But when it hits a ridiculously strong gravitational field, the light actually slows down. It has to follow Fermat's principle of least time, meaning light will always take the path requiring the shortest travel time. So, to minimize its time slogging through this thicker gravitational zone, the light actually curves away from the center of the mass. Pretty wild, right?
Now, what's really interesting here is that we can see this exact principle happening right now out in the wild with the Abell 2218 cluster. Notice those stretched out, smeared, elliptical arcs of light just wrapping around the center? Those are not just oddly shaped galaxies. Actually, scratch that. They are completely normal background galaxies, but their light has been intensely stretched and twisted by the massive gravitational field of the cluster sitting right in front of them. Astrophysicists call this weak gravitational lensing, and it's a total game changer. By measuring the exact shape and stretch of those arcs, astronomers can basically reverse engineer the picture to map out exactly where all that invisible mass is hiding.
And that brings us to the next massive question in our investigation. We see the light bending. We absolutely know there must be an unimaginable amount of mass out there to warp the fabric of space that severely. But here's the catch. When we add up all the visible stars, planets, and glowing gas in those regions, it is nowhere near enough mass to cause that kind of bending. Not even close. So what exactly is this massive invisible scaffolding that's causing such an immense gravitational pull?
Our prime suspect? Dark matter. This is essentially the invisible backbone of our entire universe. Based on our best gravitational models, dark matter consists of unidentifiable point masses that simply do not emit, absorb, or reflect light. That makes them literally invisible to every single traditional telescope we have. Yet, they make up the vast majority of the matter in galaxies. Think of it like this. Just as the planets in our solar system orbit freely in the sun's gravitational pull, these dark matter particles just sort of swarm freely within a shared galactic gravitational field, exerting a massive positive gravitational pull that anchors the whole shebang together.
To really put the scale of this unseen force into perspective, just think about these staggering ratios. In our very own neighborhood, the Milky Way, all the billions of brilliant blazing stars you see, they make up only about 5% of the galaxy's total mass. 5%. The rest is overwhelmingly dark matter, and it gets even crazier. In some dwarf spheroidal galaxies, normal, visible matter accounts for less than 1% of the total mass. Dark matter is the primary boss in most galaxies, forming these colossal, invisible halos around them. And these halos are so gravitationally dominant that they actually reverse local cosmic expansion. They literally pull gas and stars inward just to keep the galaxy from flying apart.
So, okay, we've got a universe that is absolutely saturated with dark matter. Everywhere we look, there are these massive invisible halos pulling everything inward, exerting an immense positive gravitational grip, which naturally leads us to a massive plot twist in our cosmic detective story. If dark matter is constantly pulling everything together through gravity, why on earth do all our observations tell us that the entire universe is expanding?
Enter our third and final cosmic clue: dark energy. If dark matter is the universe's scaffolding, dark energy is its invisible, totally unstoppable engine. It's a deeply mysterious force, and to wrap our heads around it, we have to look at a super counterintuitive rule from general relativity. In relativity, pressure can actually act as a source of gravity. But dark energy? It exerts a negative pressure, essentially a state of tension. And in the bizarre upside-down rules of the cosmos, negative pressure generates gravitational repulsion instead of attraction. It physically pushes the very fabric of the universe apart.
So the crucial point all comes down to the seemingly simple little number, 0.5. For the first few billion years after the Big Bang, the universe was expanding, sure, but that expansion was actually slowing down because the massive gravitational pull of dark matter was acting like a giant cosmic brake pedal. But right at the cosmic redshift of approximately 0.5, the density of matter had thinned out enough due to that expansion that dark energy finally took the upper hand. At that exact epoch in time, dark energy took over the driver's seat, and the universe's expansion stopped slowing down. Instead, it began to violently, relentlessly accelerate.
Let's move to see how this builds up, because it really sets the stage for the ultimate cosmic showdown. On one side of the ring, we have dark matter. It exerts positive pressure, generating gravity, desperately trying to pull matter together to build magnificent structures like galaxies and clusters. And on the other side, we have dark energy. It exerts negative pressure, or tension, generating gravitational repulsion and relentlessly pushing the universe apart. Everything we know, every single star, every planet, every galaxy, us, we all exist right in the crossfire of this epic, invisible tug-of-war.
Which leaves us looking ahead to perhaps the greatest mystery of all, in this endless, invisible battle between the pulling grip of dark matter and the outward push of dark energy. What will be the ultimate fate of our universe? Will dark energy just continue to accelerate, eventually tearing apart every galaxy, star, and atom, or is there another massive twist waiting for us out there in the dark? We definitely don't have all the answers yet, but every single day, by studying the invisible clues left behind, we get just a little bit closer to understanding the true nature of our reality.